So welcome back to the Power Society. So we are still on. Let's look at the simple motion. Now, if we have this as our pendulum, when this is swing, when it is swing, we will have it coming to this point A, and then it moves to B. So if we have it moving that way, so it comes here and then moves that way to the side, gets to this point, comes back. So this is to and fro, the to and fro motion. Motion. That's what's called simple harmonic motion. So in this case, as the body moves and then comes back, so it's like its acceleration is always towards a fixed point. It's always towards a fixed point. So it goes and then comes back, goes and comes. So it's like something, when it goes past this fixed point, it goes up. Something like it's pulled back again towards the fixed point. And when it goes past it, then it will come back again. So there is a constant acceleration which is directed towards the center. Okay, and that will mean the acceleration is not ever increasing. It increases and then decreases to its initial point. So that will be, you can say in that case, acceleration becomes negative. Negative. That is why it's negative. It's negative because it is not ever increasing. It goes and then comes back. Right. Now let's look at some few calculations that we can do. This is the length of the pendulum, the mass m. Okay, let's assume because this comes here, this will be the tension in it. Okay, now the displacement along this path, we'll call that displacement y. Okay, let's call that displacement y. Now, the angle that this is swung through is theta. So the angle that is swung through is theta. Okay, this angle is theta. Now, if we look at this again for this angle, going to work. There is a point, comes here, moves to this point, there is a big point. Okay, this angle is theta. This distance we're talking about is our y. Okay, so this length is the length of the pendulum, this thread or the thread that is holding the pendulum, the ball. Okay, right, now let's say this is the tension in the y. Okay, so for a very small angle, if this angle is very small, then more or less we're going to have something like that. Okay, let's say, and that's what we do to the pendulum. This part is what comes from here. So if it is very small, then this is almost y. No y is here, but if it is very small, y and this length will be almost the same. So this y, and this angle is almost 90 degrees. This is theta. Of course, this is the hypotenuse. This is the length. Okay. Now let's see the relationship. So what we are trying to do is we want to find the relationship between t. Between t, mass, ground, and length. Let's see if one of them is out or they're all in. Let's see. So theta by definition, theta in radians, is equal to, if we are assuming this is going around the circle, then theta in radians is equal to what? The distance moved, which becomes y, over the radius, which is L. This is one equation I will be looking at. So we have here theta in radians linking y and L. Now, let's assume this is the ball. When it is here, it has then put theta is equal to what? Y over L. This equation 1. Now the ball is here. When it's here, the force acting on it is mg. Okay? It will have a corresponding, it will have a component. Part of it will be here because it is, and then this is it. Okay? It is between, it is vertical. So it will have part of it tangential to the curve here. And that is what is pulling, this ball towards the center. It is the force of gravity. When this one goes up, it's the force of gravity that pulls it back. Okay? Well, the point, once you rise above a certain height, this force will bring it back. Okay? So it's this force which is bringing it back. So what will be this force then? You know this whole thing must be 90 degrees. Or if you can look at it this way, this line and this one, they are parallel. Okay? They are parallel. And therefore this angle will be equal to this angle. This angle here will be theta. If this angle is theta, then this one is going to be 90 minus theta. Okay? Okay. Now, what we are trying to do is we want to find, in terms of force, you can relate forces, you can relate length. Okay? Then you can get your, somebody can also relate velocities, somebody will relate accelerations and so on. So we are talking about forces now. Let's look at forces. This one is in radians. We have length. So this is for length. Okay? Now let's look at something for the forces. The force that is acting on this. You realize that this is mg. That's the force, vertical force, the force of gravity on this body is pulling it. That's the weight. Okay? Now this force, when it goes up, the same force has a component as part of it. Because it is here, it is acting vertically. But any force has a component in 90 degrees and has component in two angles which add up to 90 degrees. That means if I draw this like that, it will always have components in between two angles at 90 degrees, this being hypotenuse. Okay. So it depends on the direction of the force. So it will always have 90 degrees around it where the force can be felt. So within all this angle, okay, this force that we have drawn here can be felt within all this angle. So this force that we have can be felt within all this angle. That's what I mean. Okay, so if it can be felt within all this angle, what part of it is here? That is pulling, because that part is what is pulling the object towards the center again, so that it swings back and forth. Okay, so we want to find the relationship between this force, the part of it which is here. If you want to do that, you use the triangles from mathematics. Okay, this is the force itself. The force itself becomes the hypotenuse, and then this is one part of it, and then of course it will have another part in this. Right, so let's see what means then. Right, there is the hypotenuse, so this should be 90 degrees then. Okay, this should be 90 degrees. So in that case, we are interested in this length. If you are interested in this one, this angle is what we know. This is the angle we know. So the relationship between this angle, this force, and then the force here, let's say this force is force A. Now force A will be, let's see the relationship. This is the angle. The angle is adjacent, is close to this side, and then this is the hypotenuse. So adjacent and hypotenuse, we use cos. That's cos. So it is going to be cos 90 degrees minus theta is equal to, cos is what? Adjacent, FA over hypotenuse, which is mg. So from this FA is here, so this will cross and multiply. FA will be equal to what? mg cos 90 degrees minus theta. Right. Now, let's see what happens. You know that the mg here, here the ball goes, when it's going up, gravity, it's acting, going against gravity. So gravity will be negative. So in actual sense, so let me put this one here. In actual sense, Fa will be equal to negative mg cos 90 minus theta. That's why I put this one. The reason why it's negative because the gravity, acceleration due to gravity, will be acting against it as it goes up. Or you can look at it this way. So far as it goes and comes back, that acceleration here, becomes negative g. Instead of g, it becomes negative g. Because it is not ever increasing. It goes, it comes back. The same acceleration is pulling it back towards right. But as it goes up, it's pulling it back. If it's forever going to be, if you are going against a force, then you are opposite. So we will negate one. If you are positive, then the other one will be negative. So that's what we get. We'll get for that acceleration. The acceleration will be negative. So this is what we can. Now we can rewrite this one as Fa is equal to negative mg. You can write this one as sine to make it. Sine is the complement of cos. That is, if you put sine and cos together, you get 90 degrees. So if cos is 90 minus theta, then sine is what? Theta. Because if you add cos plus theta, sine cos plus sine, you get 90 degrees. So if this one is 90 minus theta, then here should be 90 theta. So that you get 90 is equal to 90, then it will cancel out. Right. So this is what you have. This is this equation 1, this equation 2. Right. Now, so we have equation 1 here, equation 2 here. Now let's look at another equation. Let's relate the sine ratio properly. So we can say that cos theta is equal to this one. So sine theta is also equal to, in terms of length, okay, in terms of length, that is going to be what? If you have theta here, when this angle is very small, when theta, this angle is very small, we can look at it. We want to relate, we want to find, we have y and l here. We want to find another relation for sine theta, which will contain l and y. Okay? Because we want to have l and y. L, of course, l is the length, okay? Either l and y in it, and then t, we'll come to t later. Right, so sine theta from this triangle. Okay, if this one is very small, then we can say almost that this one is straight and this is 90 degrees. And this is our y. Y is the displacement on this part, the horizontal part. So in that sense, sine theta will be equal to what? This sine theta. Sine theta will be equal to opposite. Opposite is y over hypotenuse. Our hypotenuse is here. Okay, which comes back as what? Your L. At this point, it comes back as your L. That is in terms of if you are looking at it, opposite over L. Because L will be almost the same thing here, because it has moved, it's almost the same thing there. Now, when this one is very small, when sine theta is very small, we can say sine theta is equal to theta. So this is also equal to theta. So you see that we come back to the same thing here. That we can. Alright. Now, having these three equations or two equations, we can put them together and then work things out. Now, we are interested in finding t. So what's the formula for t? T is equal to, or we can just formulate it like that, this way. Frequency is equal to number of complete revolutions or complete cycles over time. Now, time t, time t, which is the time taken to make one turn or one revolution. That's to go here and come back. Okay, if you go and come back one, when n is equal to 1, the time, special name for time becomes period. Okay, becomes period. Now, we have also found out that at this point, when this one is going like that, going and coming back like that, okay, this is a changing y, okay, right. Now, at the point where this ball gets to this highest point, it's actually this also the changing y, okay. Now, if you remember, if you recall, when we did this circular motion, and then we said this y. Now this is the ball. As it's going, it's making distances, okay? And this is theta, and this is the radius. So at the point that this car gets here, radius becomes equal to what? Y. That is the point I want you to. Radius becomes equal to y. So we'll come to it. Now, so we are saying that then from this one, we said y was equal to what? R sine theta. Then when we differentiated, we found the 2, the y, the x. We found out that cos theta, this was minus r sine theta. Okay? This was what we had. Now, when we had this one, we said if this is 90, when it gets to this point, it's 90, then acceleration becomes what? Negative squared r. This is it. So this is the acceleration, maximum acceleration. Okay? Right. So at that point, we can say that acceleration, which is equal to negative this, and then what's that point? It becomes y. It becomes y. Okay, that's it. So we have a, y becomes a radius. So we have put that one there. But from this acceleration, and that's it, this r. If we were to find from this side, if we were to find the complete revolution, if we were going around this one completely, if we were going around this one completely, then what you have is theta is equal to the distance that you're going divided by r, and this will become 2 pi. If we make one complete revolution, become 2 pi r. Okay, over r. So it's like theta, at that point, theta becomes this, and then you are going to get 2 pi. Now let's say omega is equal to this over t. When you make one complete revolution, is 2 pi r. But remember that the t here becomes capital T. Okay, right, and then will be let's make it this way so that you get here. Omega is equal to this 2 pi, because is theta over t. For one complete revolution, theta becomes 2 pi, and this t becomes t. There is no distance. R, if you add r, it becomes distance, so it's 2 pi for one revolution, is 2 pi. So this equation is what I want us to keep in mind. Now this theta relating time, a period here. Okay, good. So we'll be trying to get something like that in the equation. Now, so we are back to this point. Where is frequency is equal to that, and 1 over this. A is equal to this. Good. Now, the force that is bringing this one back is actually F is equal to MA, and this is equal to, the force is, we have defined the force as this one, minus mg sin theta. Okay? Now, this force that is bringing it back is what you have here. Now, we also could say that from here, this MA is equal to this. Okay? Now, let's see. We can also say A, we can represent A here by this equation, so that we have M, this is going to be negative omega squared y. So that we put A in place of A, we put this one there. So this is going to come out as what? Negative mg sin theta is equal to negative m omega squared y. Now what do we see? This m will cancel this m. This negative will cancel this negative. So that we have j sin theta is equal to this. Now we've already said, so let's come back, we can clean this part. So from here, we will now going to get j sin theta is equal to omega squared y. Now let's try and then express this one in terms of the L and the y. We know sine theta here, we said theta is the same as when theta is very small, theta is the same as in terms of radians. Theta is equal to what? Radius, which is what? L. This is radius L over what? Y. Sorry. Not the radius is theta in terms of radius is equal to the distance, which is y over L. Because this is the distance. If this is the circle, it's the distance that you have gone divided by your L, which will give you theta. Now, and of course, we said this one, if this is very small, you can say J theta is equal to omega squared y. Now, theta we are saying is that, so J times y over L is equal to omega squared y. Right, so you realize that from here, y will cancel out y, and then we're going to have what? We're going to have J over L is equal to omega squared theta. Which means if you find square root of that, square root of that, omega is going to be equal to square root of J over L. Now we want a relationship for t. We also know that t is equal to 2 pi over omega. So let's put omega here. We're going to have 2 pi over root of J over root of L, which is the same as 2 pi root of L over root of J. So this is where we are. This is where I want you to focus. So this is what you have. So from this, we're going to have what? From this, we're going to have this. We're going to have this is going to come out as what? T is equal to 2 pi square root of what? L over G. This is the equation we're looking for, and this was the first equation that we derived when we were doing we're using the dimensions to derive equations. This was the first equation. Now, so this is for pendulum. You can have a spring, a bar on it like that, and this spring will have force which is given by kx. Kx. Okay. Now, if you do the substitutions and work out, this is the constant. Because if it is hanging, there is gravity in it, there is gravity function in it. Okay, you get the same thing. Then, in this case, t will become equal to 2 pi square root of. The variable in it is the extension. Call it extension E. So, it will be extension, there is a variable over the constant. Because we have J, then it will be J here. Okay? Now, let's look at another scenario. So you can go through the processes and you arrive at the same thing. Let's go through the other type of example. So this is for the spring. If it were, let's say the spring is not, it's horizontal, so no gravity has been taken off. Okay. Then there is the mass of the spring, and it is here, it is pulled, x comes back. Okay, once it pulls x, and then f is given by negative kx. So that we negate it, so that we are saying that it will not keep on going, it will go and then come back. Okay. Now from this, there is no gravity. If it is lying horizontal on the table, there is no gravity component. Here, when it was hanging, gravity was acting, so we had gravity as a constant. So if it is horizontal like that, t becomes the same 2 pi, but the constant in this point is rather k, so k here, and then we have extension here. Now let's look at another situation where we have this one, the column. So we have fluid in its column. Okay, and this is also swinging like pendulum, going up there. So as x above it, okay. Now this will also have its constant. T should have the same equation with the constant. Okay. 2 pi. And the extension maybe x, which is varying. Okay, that can be x. Let's say assuming it is x. Okay, of course this one gravity is acting on it. Okay, then you have your, or let's put it here as a constant. Okay, of course this k will depend on gravity, and then that will be our point here. Let me put, this will be a general equation, right? This will be the variable and this will be the constant. Something. So that will be it. Okay, so in writing it, because this is, if it is hanging or gravity is acting on it, then this equation modifies to this. Okay, x can also be, we can say the height. Okay, the height, if it is measuring the pressure, then height over g. So you see that the equation becomes very, it's modified, but you can follow the trend. So the trend is t, if for pendulum, the length is there, length of the pendulum, and then we have what? Our g, and gravity is the point. Now here, the extension, the extension here, the extension of the spring, okay? And then we have gravity, because it's acting on the gravity is there. Now here, when it is horizontal, there's no gravity on it. So it is being pulled. Gravity has no components. So gravity is like that, horizontal direction. If it is exactly 90, it has no component, unless it's something within 90 degrees. Less than 90 degrees within it. That is where this force will have effect. Okay. Right. So in that case, there's no gravity. And since there's no gravity, the only constant in there is the constant of what? The spring, which allows it to expand. This is a special property of the spring itself. Okay, and that is why we have the spring constant here. Okay, the spring constant where here, as you see it here. So we have like how many equations now? 1, 2, 3, 4. So these 4 equations, if we can go through the process to derive this one and then get the extend it to get this one. Or you can derive each of them from the same principles that you have gone through. First, you have to find the force which is moving it up. Then you connect the forces with the sides, okay? Because we want something about the length, the mass, so the length of that. And assume that this is a very small, because usually we swing the pendulum in a very small angle. So you see that if you are swinging it, the time it will take this one to go and come back does not depend on the mass. It only depends on the length of the length of the pendulum. That's the string which is suspending the pendulum, the ball. Alright. So this will bring us to the end of this section. Now let's look at this in here. There's a mass. Okay, cut it down here. Like each is a mass at a distance. The mass, let's say this is the center. Okay, each mass will have a certain distance. R1, R2, and so. So this whole thing is what is forming the mass. Okay, we are going to look at rotation. So rotation is when the body itself, okay, let's say we have this whole body. Then there's a whole unit, and it's turning around itself. But this, if we have this, then this is going around it. It's going around it. Then that is different. It's going to a certain motion. But this is rotating. If it is rotating around a point in the body, if the body is moving around or turning around a point in its body, that is rotation. Okay, but this will be going around. This will be a circular kind of motion. Of course, this will also, the point here will be going through circular paths. Right, now let's look at something here. If you remember, recall from your GSS, you have pivot here, you have a mass suspended, another mass suspended. Okay, this is the pivot, the turning point, okay, on the fulcrum, right? So we usually say that your mass here, force times the distance. This is the distance. 1, 2, okay. So let's see. Alright, so we'll say F times this is a moment, okay? This moment will be equal to, should balance this. If this one is not moving, then this moment here, force and this distance, the perpendicular distance, they should balance, okay? That's moment. Now, so this using the same principle, if this is rotating, or the mass, the force that this will have, force will be equal to mass times acceleration. Right, now it is rotating. It is rotating. If it is rotating, then we know A is equal to what? Omega squared R. Okay, that is one thing that we need to remember. Acceleration is equal to this squared R. Right, so when you have this one, now we also know that A is equal to R. A is equal to R angular acceleration. Right. So from here, F will be equal to what? MP. That will be it, ME. Okay. Now, if we look at this from this angle, we're going to have this. So we can say that in place of this, F will be equal to let's put this one there. It becomes what? R omega. The reason why we are bringing the angular acceleration is we want to find a relationship, because this is rotating. When something is rotating, what becomes important to be the angles that are changing. So we want to find this in this, and then angular. So the angular component is what we are trying to find in this one here. But you realize that this F is equal to this. So if you look at it, the rotational angle, you realize that the actual force in this rotating body will be mr, because this is like its equivalent acceleration. Then the actual force in this will be mr. Now let's look at it, because when a body is turning, the actual force in it, we call that torque. The turning force, the turning force is called torque, and that turning force is equal to F times the distance from the center. Okay, so that is R. So in this case, the torque, or the turning force, which is the actual force which a body rotating